Welcome to Mythosium, the channel where we take the deepest, most misunderstood scientific ideas and turn them into clear, intuitive stories. Today we're exploring a concept that shapes everything. Every storm, every collision, every star, every chemical reaction, and every moment of your life. It's one of the most fundamental ideas in physics, yet it is also one of the most misunderstood: entropy. Entropy is often treated as a synonym for disorder, or something that explains why things fall apart. But the true idea is far richer and more profound. Entropy governs the flow of energy, determines what processes are possible, sets the direction of time, and may even be the reason life itself can exist. It is the quiet law that guides everything from boiling water to the evolution of the universe. To understand why entropy can seem so confusing, imagine asking a simple question. What does Earth get from the Sunday? Most people say energy, and that's true. Earth receives a constant stream of energy from sunlight every day. But if you think more deeply, you realize that Earth must radiate just as much energy back into space as it receives. If it didn't, it would heat up indefinitely. For most of Earth's history, the incoming and outgoing energy have been roughly balanced. So if the amount of energy doesn't really change, what are we actually getting from the Sunday? The answer is subtle. We're not getting more energy. We're getting more useful energy. A special concentrated form that allows life, weather, and chemical reactions to happen, and that deeply connects to entropy. To see how the idea emerged, let's step back into the early 1800s, when steam engines were reshaping the world. Nations depended on them for transportation, mining, and manufacturing. Engineers understood that heat flowing from something hot to something cold could be used to do work. But they didn't know the limits of this process or how to maximize efficiency. That's where the key idea of the heat engine comes in. A conceptual machine that moves heat from a hot reservoir to a cold reservoir and extracts useful work along the way. If you imagine a chamber of gas with a piston attached to a wheel and connected alternately to a hot source and a cold one, you can visualize how heat causes the gas to expand and push the piston, then later cools and compresses. This cycle converts some heat into motion. What's powerful about this ideal model is that it's perfectly reversible. If you ran the cycle backward, heat would flow back from the cold region to the hot region powered by the flywheel. The entire process could be undone without any extra energy. Everything works out exactly, step by step, with nothing lost. And yet even an ideal engine like this cannot be perfectly efficient. You never get all the thermal energy turned into useful work. A certain fraction of the heat must be dumped into the cold side, because returning the piston to its starting position requires compressing the gas, and that compression always pushes some energy out into the cold reservoir. No matter how perfect the machine is, the efficiency depends only on the temperatures involved, not on the design. To reach 100% efficiency, you would need an infinite hot temperature or absolute zero on the cold side, neither of which is physically achievable. The insight that even a perfect engine cannot reach perfect efficiency was revolutionary. It meant there was a new law of nature at play, one not captured by the usual conservation of energy. Something else was happening. Energy was conserved, but its quality was changing. That realization led to entropy. In everyday machines, additional irreversibilities appear. Friction converts useful motion into heat that disperses into the environment. Heat leaks through walls and axles. Energy spreads out, becoming less concentrated and less capable of doing work. Even though the total amount of energy stays constant, its usefulness decreases. Entropy is the measurement of how spread out that energy is. When energy is highly concentrated, like heat stored in a hot metal block, it can be used to do useful work. But when that energy disperses through the surroundings, raising the temperature of many atoms just a tiny amount, it becomes harder to use. The same energy is still there, but it's less available. Entropy is a measure of that dispersal. As scientists explored this deeper, they recognized a general pattern. The total entropy of a closed system always increases. Energy spreads out, mixtures blend, hot things cool down, and gases expand. The universe evolves towards states that are more probable and more evenly distributed. The idea becomes clearer when you think in terms of microscopic arrangements. Imagine two small blocks, one hot and one cold. Heat is nothing more than energy packets jumping between atoms. When the blocks touch, energy packets hop back and forth randomly. Every configuration of those packets is possible, but some are far more likely than others. There are many arrangements where the energy is spread evenly, but only a few where one block holds most of the energy. If you wait long enough and check at a random instant, you'll almost always find a more even distribution. That's not because heat can't flow from cold to hot. It's because the reverse is enormously improbable. In tiny systems, the unlikely can happen. But in a system with trillions of atoms, the improbable becomes effectively impossible. This statistical imbalance is what gives rise to the arrow of time. At the microscopic level, physics doesn't care which direction time flows. The equations work just as well backward as forward. Yet at the human scale, we see ice melt but never spontaneously reassemble. We watch cups shatter but never reform. We experience memories of the past but not of the future. These asymmetries come from entropy increasing. But if entropy always increases in a closed system, how do we get complex structures like planets, storms, ecosystems, and life? Shouldn't everything tend toward uniform lukewarm sameness? The answer is that Earth is not a closed system. It receives low-entropy energy from the Sunday and radiates higher-entropy energy into space. This difference in entropy allows remarkable things to happen. A key way to see this is through photons. The Sunday sends Earth high energy, highly concentrated photons. Earth radiates many more low-energy photons back out. For every photon Earth gets, it emits about 20. That discrepancy is the heart of why life can exist. Plants take those energetic photons and use them to build complex molecules. Animals use those molecules to power movement and growth. Every phase of life, eating, breathing, thinking, is a way of converting organized energy into more disordered energy. Life accelerates entropy production. Some researchers have even argued that life itself may be a natural consequence of the second law. Systems exposed to a steady supply of low-entropy energy tend to evolve structures that dissipate that energy more effectively. Over long periods, this could favor the emergence of more complex, more efficient dissipators. In this view, life is not a violation of entropy, but an expression of it. For where did the Sunday get its low-entropy energy? Ultimately, from the universe itself. If the total entropy is increasing with time, then the universe must have started in the state of extraordinarily low entropy. The scene's strange because the early universe was nearly uniform, same temperatures, same density everywhere. Uniformity might sound like high entropy, but gravity flips this intuition. Gravity favors clumping. A uniform distribution is actually extremely improbable. As matter clumped into stars and galaxies, vast amounts of gravitational potential energy turned into heat, increasing entropy dramatically. Later came a profound discovery. Black holes have entropy too, and an incredible amount of it. Their entropy is proportional to the area of their event horizons, not their volume. Massive black holes contain far more entropy than all the stars, gas, and radiation in the universe combined. This means that the early universe had an almost unimaginable low entropy compared to today. We live in the middle of this long transformation, from a smooth, low entropy beginning to an eventual heat death trillions upon trillions of years from now, when the universe will reach a state so uniform that time loses its arrow. Nothing useful will ever happen again. But the middle is where the magic happens. When milk swirls into tea, the moment of mixing contains the most intricate beauty. Both low entropy and high entropy states are simple. It's between them, during the transition, that complexity flourishes. That's where life lives. That's where stars shine. That's where thoughts happen. Entropy doesn't just tell us why things fall apart. It explains why anything interesting can arise in the first place. It reveals the hidden logic behind every transformation, from a cooling cup of tea to the evolution of galaxies. I'm Mythosium. We believe that once you understand ideas like entropy, the world becomes far more intelligible and far more astonishing. If you enjoyed this journey into one of physics' most profound ideas, make sure to subscribe for more clear, accessible science every week. Thanks for watching, and stay curious.